Um, I mean, a lot of the skills are still necessary, just not as frequently. So, sketch the slope field. When I ask you to do it given a lattice of points, I'm looking for some level of precision. So, a table of values is pretty useful when it comes to that. In this case, it looks like I'm dealing with varying x and y values. So, I would indicate, because my goal here is to determine what dy dx is, I'd indicate what x and y are, and then the corresponding dy dx. My lines weren't looking so hot. All right. So it really just is a question of how much you actually want to do on paper and how much you want to do on your calculator. So in terms of the x values, I would just go through and list them all and the corresponding y values. So I have a -2, 0. I have a -1, -1, -1, 0, a -1, 1, 10. I got to keep going because I got more. -1, I'm sorry, 0, -1, 0, 0, 0, 1. We can get a couple more in there, I guess. 1, -1, maybe just one more. Continue. Yeah, 1, -1 is where I left off, so 1, 0, 1, 1, and then 2, 0. All right. So basically, I just indicated every ordered pair of every dot that's on this lattice. All right. These are little arrowheads for those. All right. So counted for everything. So now it's just a question of, okay, how do you want to do it? Do you want to just plug it in by hand and do it? Not terribly difficult. Do you want to use a calculator shortcut? And, you know, shortcuts, I mean, they are what they are. Sometimes they're not much of a shortcut for certain situations, but in other situations they're like lifesavers. So what I would do here is go into my stat plot. I'm sorry, not stat plot, stat editor. So I'd hit the stat key and then select edit. I mean, it's conceivable that a lot of you have gotten to this point without ever really doing much inside this menu. If you haven't taken a stat class, you might never have been in this menu. All right, so stat edit. In my L1 column, it's basically like a mini Excel spreadsheet with all the functionality of it. Actually, in some ways more functionality and in a lot of ways less. But basically, I'm just going to type in every x value I have in the order that I have it. So I'll type in a -2, then a -1, 3 times, then 0 3 times, and a 1 3 times, and then a 2. All right, so my L1 column is made up of all the x values. If I hover over the, well, hover, if I scroll right onto the L1, you can see the array of values. All right. In my L2 column, I'll put in all my y values, so all the corresponding values of y. So the 0 goes with the -2. That's the way we have it here. So -1 with a -1, a 0 with a -1, a 1 with a -1, and keep on going down the line. So every pair of values in L1 and L2 should correspond to the ordered pairs that we have in our table. All right? Or tables. L3 is where the magic's going to happen. That's where you do your calculation. And again, you may not think it's necessary to do it for this particular problem. All right. But when I throw in a wrinkle, instead of dy dx equals 1 plus y over x, it's 1 plus e to the y over the arcsine of x. Now all of a sudden you do want to use this technique. All right, so a little motivation for it. So what I do is I go right up onto the L3, the column heading L3, and hit enter. What that does is it allows me to apply a rule for the entire L3 column. I want this to be my rule. All right, so all of my y values are stored in L2. All of my x values are stored in L1. So all I have to do is get that rule in there, get that relation in there. So I have L3 equals blinking cursor. I'm going to type in, I'll put parentheses, 1 plus L2. Right above the 2, you can see it right there is the L2. I get it by hitting second 2. Close the parentheses, divide by, I want to divide by my x values, which are all in L1. I get that by hitting second 1. All right. So it's going to take every value that's in L2, add 1 to it, and divide by every value that's in L1. That's the one drawback to the approach. Hopefully it's going to break. Dang it. It broke. All right. Well, in the cases where x is equal to 0, it's not going to work. And that is still not a waste of time completely, but it sucks. Is there a way around it? You just get the zeros out of there, right? All right, so anything with an x value of 0, you got to ditch. It's annoying, but it'll save it. Delete, delete, delete. Delete, delete, delete. All right, so let's try that again. You'll just have to do the zeros by hand. In reality, we already knew those anyway, right? You don't need a calculator. For these, you didn't really need a calculator for much, but it's pretty obvious that 0 on the bottom is going to give you undefined. So, undefined. So, as adjustments go, that's not the worst in the world, I guess. 1 plus L2 divided by L1. Now it's going to work. So it gives us all our slopes, and we could just run through and jot them down. That's assuming you even want to jot them down. You know now that you need a slope of -1/2 at the coordinate -2, 0. A slope of 0, a slope of -1, a slope of -2, a slope of 0, 1, 2, and 1/2. All right. So, moral of the story there, I suppose, is just make sure you account for anything that would be undefined or imaginary. That could happen too. And then once you have those accounted for, everything else goes in your calculator. If you like this method. If you don't, then whatever. 0, -1, so I'll get those undefineds in there. 0, 0, and 0, 1. I'll get my zeros in also. I think there's only, 2 of them? So at -1, -1, slope of 0. Add 1, -1, slope of 0. So now we just need reasonable estimates of what the other slopes would look like. And you know, you use a sheet of paper. Pinky is perfectly fine. All right, so if I'm looking at -2, 0, here's -2, 0, I need the slope of 1/2. So that would be this line segment. So I'm just ballparking it. That's what, just get an estimate of what the, I broke out the ruler last time. That takes forever. Get an estimate of what that slope looks like. We need a slope of 1/2, negative 1/2. I went the wrong way. Down 1, right 2, and then just slide your finger over and draw a little line segment. All right. At negative 1, 0, I have a slope of negative 1. So pinky action there. Kinda. At 1, negative 1, it's a slope of negative 2. I'm sorry, negative 1, 1. It's a slope of negative 2, so that's all right. At 1, 0, it's 1. At 1, 1, it's 2. That is the question. Well, can't be a parabola, right? Because a parabola never goes vertical. We need something, we need a type of function, and it's going to have characteristics that allow the slopes to go horizontal and vertical. Pretty much be positive, negative, horizontal, or vertical. You got to think about, well, what kind of function would do that? I mean, what's the simplest function that could do that? Like a rational function? No, even simpler.
It's like 1 over x, but 2 over x.
Like a conic section, a hyperbola? Well, that sounds like a hyperbola. If it's a 1 over x, but kind of rotated, so like,
But
so
still
that's like,
astronomically approaching it, so
yeah, that's a hyperbola, which is by definition not simple. The tables? Yeah, it should generally appear to be steeper, but I'm not sitting there with a ruler. Based on my first glance, when I look at it, if it looks about right, you're getting pulled.
Wait, how does it go? It goes
it's back. It's flat. It's undefined number, and it's not positive anything. So it has to be like symmetric both again.
Now, bear in mind, it doesn't have to be a single function that has all of these slopes occurring at the same time.
There's a function that has all those slopes.
1 over x cubed. There is a very simple function that can have a slope that is undefined, a slope that's positive, a slope that's negative, and a slope that's 0. Or a slope that's 0.
1 over x squared.
Let's solve the differential equation and see.
Oh.
Again, those slopes don't have to all be occurring in the same function. It could be maybe one version of the function has just a positive slope at all times. Maybe one version of the function has negative slope. 0, undefined. So, let's rewrite it. We have dy dx is equal to 1 plus y over x. I need to separate my variables. I need to get the x's together and the y's together. So I'm going to do a quick switcherooski on these two bad boys and get a 1 over 1 plus y. That looks terrible. One over x dx. Now you look at that and you say, well, that's terrible. There's no way that's going to lead to a simple function. And I'm telling you, simple function. Very simple. What's the antiderivative of 1 over 1 plus y? Say it again. Natural log of 1 plus y. And the other one is the definition of a natural log, right? So, yeah? I need to get the y alone if possible. Sometimes I can't. If it's a conic section, like an ellipse or a circle or something like that, then you might have a standard form that's more appropriate for that. But in this case, I'm going to write it as log base e of 1 plus y ln x plus c. Convert it over. So we think of this as e to the ln of x times e to the c. That's an e to the c. And e to the c is what? That's a c, yeah. So c e to the ln of x, absolute. All right, quick Q here. What's e to the ln of x? Just an x. So c, the absolute value of x. Couple of avenues that you can take from here, but both of them, both avenue or any avenue, really requires you to evaluate the absolutes, because I got to account for the possibility that x can be positive or negative, and y can allow or can result in an expression that's positive or negative. So either way, I have to account for that. So what I would do is write this in each possible way that I can. So I'd write it with all positives. 1 plus y equals cx. Negative 1 minus y is equal to negative cx. Negative cx. Because absolute values are plus or minus. So I indicated the whole thing. But then when you really think about this, well, aren't these the same thing? If I'm negating both sides, I'm not really doing anything. So that second part is really unnecessary. Not needed. All right. I could just negate the left-hand side, but leave the right-hand side positive. All right, so reason that out for a second. Let's say I wanted to solve for y. I can divide both sides by a negative 1, right? That would give me 1 plus y equals, well, what's c divided by negative 1? C, right? It absorbs the constant. So I get cx. So that's the same thing. Basically, what I'm getting at here is any variation of plus or minuses that I can incorporate into this, they're all going to lead me back to this. Because my one final variation would be to leave this positive and make that negative. Negative cx becomes cx. Bottom line is I get this equation. Y equals cx minus 1. Which is what kind of function? It's a linear function. Can a linear function have a positive slope? Can it have a negative slope? Can it have a 0 slope? Horizontal? Sure. Can a line have a slope that is vertical? Or a slope that is undefined, making it vertical? Yeah, it just wouldn't be a function anymore, right? But there was no requirement that it actually had to be a function. Well, then we would eliminate that possibility. So then, but that's good because we're dealing with a situation here where we're not looking at a slope that's undefined anyway. So now, if I need to find my particular solution, I'm working off a general case, and I wrote too big. Lock in place. Now I just need to plug in my x and my y. So 1 would be equal to c times -1 minus 1. Here we treat c as a variable because we're looking to solve it. Because if we didn't, c would just absorb everything and we wouldn't get a meaningful solution. Sorry? Why can we? Oh, that was my whole explanation. So, just one more time. If you say why can we just drop the x or why can't we just drop the x?
Why can we just drop the absolute value?
Oh, the absolute value, yeah.
No, we have to keep the absolute value.
Yeah, no, I misspoke. All of this is why we can. Because no matter what variation of positive or negative we get, it all bounces back to this expression. I didn't include the last one. The C will absorb the negative. Because it's the absorbing constant. C absorbs everything. Alright, so we're going to get 2 equals negative C, making C equal to -2. And therefore we end up with y equals -2x minus 1. Alright, so that would be the particular solution. It does satisfy these requirements. If I plug in a -1, I do get a 1. And also, the slope field was telling us, and really we don't even need to plot it on there, it just gave me a sense of what I'm looking for. That I'm looking for a function that could have positive slopes, negative slopes, zero slope, or no slope. A linear function does, or a linear equation will do that. This particular one would have a negative slope, so if I plotted it at -1, 1, it would be in this location and it would follow this pattern, so you'd be looking at something like that. All right. There's a whole lot more to slope fields that you get into in differential equations, but this is just really the smallest taste of it. Ton of problems here to practice with, some more difficult than others. In numbers 1 through 6, you kind of, I mean, it's up to you, but you can kind of skip that if you want, just because it's saying decide whether it can be separated. It's just, in a lot of cases, it can't be separated because I can't separate it. Like, I can't get y and x alone, on either side. But the short answer to it is, if it's not a proportional relationship, then you're not going to be able to separate variables. You need a different technique. And that's what we'll get into next class, which is something called the homogeneous differential equation, which is how you separate out variables that don't seem like they can be separated. So, there's a ton of problems here. Try a couple. You don't have to go too crazy with this. But in terms of lecture, that's where I'll leave you. What I wanted to do now is go over the tech assignment. This one should actually be pretty quick because there's no program to download. So that's exciting.